for a few years, jointly between Scripps and Hawaii, but has been at the University of Miami since 2003. And she's now a full professor and the Associate Dean for Research at the University of Miami Rosenstiel School of Marine and Atmospheric Sciences. She's been doing some really interesting work in the Agulhas Current and the Somali Current for many years now. We overlapped. I was doing that stuff back in the 80s and 90s, and she's been doing it ever since. As she said, that the Indian Ocean wasn't big enough for the both of us. She's going to tell you about some of the time series measurements they've been doing in the Agulhas Current and how it's related to our changing climate.
All right. Thank you, Mark. Thank you so much for inviting me. It's been a very nice couple of days, yesterday on a boat and today talking to many of you. So I've learned a lot about sea level. I'd like to follow up on. So yeah, what I'm going to talk about today is the Agulhas Current in a changing climate, and I'm an observationalist. So what I'll be showing you is based on observations from the ocean, in situ observations and satellite observations. And so I realized that here probably the current is a relatively unfamiliar topic. The Agulhas Current, of course, is a western boundary current. And so we might first ask ourselves, what are we expecting to happen to western boundary currents with climate change? How are we expecting them to change over time with the trends, with the forcing from carbon dioxide? And so we might look at, this is from a paper by Wu et al. From 2012, who showed this is the sea surface temperature trend minus the global trend from the HAD SST2. And what you can see here is that the western boundary current regions light up in terms of this warming trend over the last 100 to 150 years. And you can see these regions light up also in terms of heat content, 0 to 700 meters in the last IPCC report 2013, a figure by Monica Ryan. And so the question is, what's going on here? Why are these regions heating up at 2 or 3 times the rate of the other parts of the world's oceans? And some of the theories have been related to the winds. And this is also from Wu et al. They looked at the wind change between 1900 and 2008 in this reanalysis, the 20CR version 2. And they see a significant change in the trend. This is plus or minus the trend, with a strengthening of the westerlies and of the trade winds over the last century. And so if the westerlies and trades are intensifying and we're seeing these sea surface temperature signals, then is there a poleward shift and or intensification of the western boundary currents? And this is what Wu and others have argued, that the winds are forcing through linear dynamics an expansion of the subtropics and or an intensification of the western boundary currents through sphere-drought dynamics. And that's causing these strong signals in sea surface temperature and upper ocean heat warming in these regions. So in that case, we might go to the Agulhas and say, I'm expecting the Agulhas to be intensifying over time. So why do we care about understanding how western boundary currents are changing? Well, western boundary currents are regions of the ocean that have a very strong negative heat flux. So in other words, the ocean is forcing the atmosphere really strongly in these regions. And you can see that in this data set, which is the mean net surface heat flux in watts per meter squared from Megan Cronin. And you can see the Agulhas system here, the Kuroshio, the East Australian current, the Gulf Stream, and the Brazil current. All regions where the ocean is forcing the atmosphere strongly. So the ocean is pumping heat and moisture into the atmosphere in these regions. And for example, many papers have shown for the Gulf Stream that these systems actually guide the mid-latitude storm tracks. So that's one reason why it's important. Another reason is global heat balance. So the ocean's role in global heat balance is shown here, and basically there's a meridional heat flux from the ocean north and south. So a meridional heat flux whereby the ocean is cooling the tropics and warming the poles. And a major carrier, of course, of this heat transport is the western boundary currents as part of the global meridional overturning circulation. So western boundary currents carry a lot of this heat meridionally as they flow away from the equator and towards the poles. Okay, and therefore they're an important part in moderating the temperature of the climate, cooling the tropics and heating the poles. So we might think that if these areas are intensifying in their strength and in the amount of heat they're carrying meridionally, that could be an important feedback on climate and climate change. So with the Agulhas in particular, what do we see happening? This is a zoom around South Africa of the SST trend over the last 2 decades from the 1980s to 2000s. And you can see that this region, like we saw in the global picture, is heating up. And we can see here, this is the heat flux from the ocean to the atmosphere this time, so positive heat flux into the atmosphere. And you can see that this is a region that's warming up, or where the ocean is warming the atmosphere. This is actually also the trend, okay, in this heat flux. So this is a region where the SSTs clearly aren't just increasing because of how the atmosphere is working on the ocean, but the ocean is actually working on the atmosphere. And so in this paper by Ruel et al., they theorized that there must be an intensification of this system bringing more heat into this region, okay, over time. And the Agulhas current and the Agulhas system is connected globally, of course, within the global thermohaline circulation. And what this picture shows is this region of the southern hemisphere supergyre. Okay, this is the 0 to 2000 dynamic height. So you can see this region of the southern hemisphere supergyre actually stretches across the South Atlantic, the Indian, and the Pacific, with an influx from the Indonesian through flow. And the Agulhas current feeds into this choke point where there's a retroflexion in the current. Most of the flow returns, of course, around the subtropical gyre of the Indian Ocean. But then there's this leakage into the Atlantic via eddies and mean flow as part of this supergyre, okay? And it carries warm and salty water. So the waters in the Indian Ocean are more salty than those in the Atlantic. And there's been some model studies, climate models by Wire, more recently ocean model hindcast by Biasztok, that show that this leakage has an effect on the Atlantic meridional overturning circulation. So the idea is this is the so-called warm water route, where waters are fluxed into the basin, they're warm and salty, and they reach the North Atlantic, and those salty waters are going to tend to force a stronger overturning. So these hindcast models, with their shift in the westerlies, have suggested that this Agulhas leakage is increasing over time, since the 1960s to the present day. And if that's the case, then we might imagine that that's going to be a positive forcing on the AMOC, on the Atlantic meridional overturning circulation, causing it to intensify potentially. What we know from climate models, or what we think we know from climate models, is in fact that the AMOC may be weakening now and over the next century because of ice sheet melt in the northern hemisphere. So that's adding fresh water in the polar regions, whereas the Agulhas system is adding salty water in the southern hemisphere, subtropics, okay? So you can think of these two inflows as kind of opposite forcing on the AMOC, and so there might be some bounce here in terms of how the Atlantic meridian overturning circulation changes in the future. Climate models don't resolve the Agulhas retroflexion. So climate models have an Agulhas leakage which is biased 3 or 4 times larger than what we estimate it to be from observations. So it could be a pretty interesting region where Agulhas leakage might potentially act against ice sheet melting in terms of forcing the AMOC in the future. Okay, so hopefully I've convinced you that it's an interesting region to look at. A lot of this is fairy tales, right? It's all models. But there is a little data to back up these ideas, and it comes from some paleo cores taken from ocean sediments in this region. And we're going to look at the CBR core in particular that was worked on by Peters et al., 2004. And what they did was they went back 500,000 years, and you can see basically they've got a number of glacial interglacial cycles in this 5,000 years. This is the delta 018 or ice volume proxy at the top. And they looked at a proxy for Agulhas leakage by basically looking at what the current assemblage of fauna in the Indian Ocean is today, okay? And going back over time and looking at how much of that fauna they could find on this Atlantic side within the Agulhas leakage, kind of like the northern part of the Agulhas leakage corridor here. How much of that fauna was from the Agulhas over time and how it changed over time. And they also used assemblages of subtropical and subantarctic fauna to look at how the subtropical front, okay, approximated by this white line here between the subtropics and the subpolar gyre, how that was changing and shifting in time. So what they found was that the subtropical front begins to shift south, okay, and this is the solar forcing in pink, and this is their subtropical to subantarctic fauna ratio. And the sea surface temperature increases. This is at the glacial interglacial transition. And then there's this strong peak in the Agulhas leakage, this strong peak in the amount of Agulhas fauna over this sediment core. Ice volumes rapidly decreases, and then using delta C13, you can estimate the deep water oxygenation or the ventilation of the ocean over time. And so they argue that then there's this strengthening of the overturning circulation in the ocean. So at least on paleo timescales, there's some observational evidence that Agulhas leakage is an important part of the way things change over time and may precede strengthening of the MOC. Okay, so coming back down to the Agulhas Current here and now, I thought I would give you a brief history as a little interlude. So the Agulhas Current was discovered around 1500 by Vasco da Gama, this guy who looks like a real gentleman, but he was actually rather a tyrant, and exploited the Indian region for silks and spices on behalf of the Portuguese. And it was mapped or charted for the first time by a cartographer from the UK, James Rennell. I looked up this information in the library at the National Oceanography Centre when I was a student. You know, it was fascinating because they have the original pilots in there, you know, that dates back to these times, describing what they saw in the ocean. And it took 2 centuries later until we got the first full-depth direct measurements of the Agulhas Current using an instrument developed by Eric Fearing at the University of Hawaii called the Lowered Acoustic Doppler Current Profiler. Until then, we'd had geostrophic estimates, which of course suffer from the reference level problem. And so we really didn't know, for example, that the jet was V-shaped, that there was an undercurrent, and so on before these measurements in 1995. And this was the era when I was a student and I first went to the Agulhas Current. So it was a pretty exciting time. So what I wanted to do was try to look at how the Agulhas Current is changing over time. And of course, I don't have a long series of data to tell me what's going on. And even if I go and put in all my moorings, which I did, I'm not going to get paid to do that for 20 years, or I might if I'm lucky. But you know, I was like, how can I leverage a bunch of data over a fundable period of 3 years in this case to give me a longer time series? And so what I did was basically plan a transect along a satellite ground track, okay, along an altimeter ground track. So I went to about 34 South, where I have a ground track coming off land, almost perpendicular to the current. It's about 15 degrees actually to the mean current, and from perpendicular with the coast. And we put these moorings along that ground track, 7 full depth current meter moorings, A through G, and 4 CPIES, that's inverted echo sounders equipped with current meters and pressure sensors on the outer part of the array here. And the idea of those was to capture meander events in the Agulhas Current. So meander events were well known in the region where the current separates completely from the continental slope and shifts 100 kilometers or more offshore. And these kind of mesoscale events, of course, would be missed by this current meter array out to G, which is about 200 kilometers long. So the CPIES enable us to estimate the geostrophic transport through them during these meander events and not miss the transport when they're going through. So this is what the array looks like in depth. This is the African continent and the shelf and slope region out to 300 kilometers offshore. You can see the depth goes down to 4,500 meters here. And our 7 current meter moorings are up to 4,000 meters long. We were brave enough to deploy them in this very strong current off of the east coast of South Africa during 3 cruises. So the instruments that we have, you can see pictures here on the right. This is a Nortec single point Doppler current meter, so it works through acoustics and just measures the current at one single point about a meter away from the instrument. And that's all these blue rectangles here. At the surface, we have upward-looking acoustic Doppler current profilers. So again, acoustic current meters, this time they profile from the depth of the mooring here up to the surface. Okay, so we're keeping the moorings well below the surface where we've got these extraordinarily strong currents and of course sea states. This is the CPIES. So the inverted echo sounder basically is going to transmit a pulse up to the sea surface and back down again, and give through that what's called round trip travel time, because sound waves change with the heat in the ocean. We can get a measure of heat content, okay, from those. And we can even do better than that, and I'll talk a little bit more about those later, how we get the geostrophic transport. So you can see those extending the array offshore. We had a pair of them around mooring G so that we could see if it worked. Okay, we could compare our CPIES data with the full depth mooring. And then finally, these guys are the acoustic releases. At the bottom of each mooring, 2 for insurance, just in case one doesn't let go when you want them to come back up and collect your data. We have the second one. So did it work? All right, what you want to know, and you got some clue here because this shows you also the mean velocity section of the current over those 3 years. So you want to know if your array has captured the scale of variance in the flow. So this is this shows the horizontal separation distance. So we basically looked at cross correlations between pairs of current meters in the horizontal and in the vertical to give us decorrelation length scales. And you can see that the mooring separations are in general larger than the decorrelation length scale, smaller, sorry, than the decorrelation length scales. So the scales of variability also change between deployments. So I'm showing deployment 1 in blue versus deployment 2 in red. And you can see that the length scales change during the first deployment. The horizontal and vertical length scales tend to be longer. That's basically because we had a lot of meander events during the first deployment and not during the second. In terms of the CPIES, in principle, you can take hydrographic profiles from your region and you can create a lookup table basically between dynamic height, actually specific volume anomaly, but you just integrate that for dynamic height and the round-trip travel time. Okay, so you can create a lookup table with the hydrographic data that you have in the region, and then you kind of just look up a profile, a density profile, using the round-trip travel time. That's the idea of the technique. Now, of course, round-trip travel time is one number, and you're giving yourself an entire density profile, and so sometimes there's some ambiguity, all right, in that. There might be a couple of density profiles that fit your round-trip travel time, for example. Or what tends to happen at the surface, where you can see this error in this technique increasing, is that you're not able to capture, say, the seasonal variability in the region because you just don't have enough hydrographic data. So suffice to say that you do have some errors in this technique. And if anybody's